The process of differentiation was discovered by Isaac Newton and Gottfried Leibniz in the 1600s. This method allowed us to find the instantaneous rate of change at a single point, rather than the slope between 2 points. This revolutionized not only mathematics but the world itself. Unfortunately, both Newton and Leibniz created differentiation at the same time, although in different countries, which resulted in disputes regarding who deserved the credit. What is the derivative? The derivative is a function that provides the slope of the line tangent to the curve at a particular point. To find the derivative, we use the process of differentiation. A tangent line is a line that touches a curve at only one point. But wait a minute. If the derivative is supposed to tell you the slope at each tangent line, how can we know the slope if we only have one point? In fact, we need 2 points to know the slope of a tangent line. If we want to know the slope of a specific tangent line at a specific point x, we can choose a second point on the curve and connect the 2 points with a line called the secant. Let's call the second point x plus h, because the second point is h distance away from x. The first point is at coordinates x, f of x. The second point is at coordinates x plus h, f of x plus h. Now that we have 2 points, we can use the straight line formula to find the slope of the secant. M equals y2 minus y1 over x2 minus x1. Plugging in the points into the straight line formula, we get f of x plus h minus f of x over x plus h minus x, which simplifies to f of x plus h minus f of x over h. So let's remind ourselves that m equals f of x plus h minus f of x over h is the slope of the secant line. However, we are not yet to find the slope of the tangent line at the point x, f of x. The secant slope that we have just found is just an approximation of the tangent line. So how can we find the slope of the tangent line? We can do this by making the distance h between the first point and the second point smaller and smaller. And we find that as we bring the second point closer and closer and closer and closer and closer and closer and closer until the secant becomes more like a tangent, we can make the distance between the first point and the second point very small by using the limit as h approaches 0. The limit as h approaches 0 finds a distance between the first point and the second point, such that the distance is getting smaller and smaller, thus eventually approaching 0. Now, we've got a fairly good approximation of the slope of the tangent line. The equation we have just found is the formal definition of the derivative, also called first principles. So to recap, the derivative is a function that provides the slope of the line tangent to the curve at a particular point.
The rules of differentiation are a byproduct of first principles. However, it is a much simpler and more commonly used method to find the derivative. The first and most important rule is the power rule. All you have to do is bring the power out to the front and reduce the power by 1. If there is a constant multiplied in front of a term, in this case it is 3x cubed, we keep the constant separate and differentiate the rest of the term. This is called the constant multiple rule. Now, if a constant is not attached to a term, we use the constant rule where the derivative of c is 0, where c is a constant. Putting all the rules together, we can differentiate the function. Another rule is the product rule. This rule is used when one factor is multiplied by another factor. For example, x squared times x plus 2. To find the derivative of the two functions multiplied together, we have f of x multiplied by the derivative of g of x, and add g of x multiplied by the derivative of f of x. After working out the derivatives of these functions, we sub them and the original functions back into the product rule formula. The quotient rule is used to find the derivative when one function divides another function. We differentiate the numerator and denominator separately, and then we sub these variables back into the quotient rule. The chain rule is another important method of differentiating, as it saves time. It is used to find the derivative of composite functions. The chain rule is the derivative of x, f, with g of x left alone, multiplied by the derivative of g of x. For the first step, we use the power rule to bring down the power of f of x to the front and reduce the power of f of x by 1. In the second step, we find the derivative of g of x. Finally, we then multiply f prime of x by g prime of x.
Looking at the big picture, beyond the mathematics tutorial room, differentiation is extremely helpful in the real world, with scientists and researchers across the globe using it to solve problems in their fields. Differentiation will be applied in many ways, and over the next few slides, we will show the areas and occupations where it may play a role. In the financial world, companies use differentiation to maximize profit gain by selling certain products at optimal prices. In the sporting world, differentiation can be used to measure the motion of an object, such as a basketball, and its parabolic trajectory as it moves through space during a shot. This is done by finding the speed of release required to score certain shots in different areas of the court. Exponential functions can be used by governments and epidemiologists to estimate population growth, by environmentalists to measure overall species decline, and by scientists to measure the radioactive decay of certain elements and compounds. Logarithmic functions can be used by occupational health and safety officials to measure the loudness of new power tools in different trades, and then making recommendations to wear earmuffs when using tools that exceed the safe decibel range. Logarithmic functions are also used to measure the intensity of earthquakes, potentially allowing governments to evaluate previous disasters and plan to protect against future potential earthquakes.